Okay, in this video I want to talk about a substance, an amphoteric substance, that can behave as an acid or a base in water, and then we're going to put it in distilled water, and we're going to figure out which one of those two things it's actually going to behave as. So the substance, just as an example that we're going to use here, is going to be sodium with a phosphate and one hydrogen. That. So when this decomposes in the water, we're going to end up with sodium ions, and they're not phosphate ions. I don't know if that's biphosphate, or I don't know exactly what to call that, but phosphate ions with one hydrogen on them. So this is the conjugate of NaOH, which is strong, which means effectively for the purposes of our acid base, that's just going to stay as Na+, and we're not interested in it. But this is the ion of interest here. So we have PO4, not PO3. PO4, 2 minus. And let's just give it some sort of concentration. Let's say that we had 0.2 molar this, and so we have 0.2 molar HPO4 2 minus. So I'm going to just look at what that can do when it reacts with water. So first of all, it can behave as an acid, donating its proton to water. And phosphoric acid would have started with 3 hydrogens, and this is the last of these 3 hydrogens. So if this, hold on, I'm going to give myself a little more space and talk about this carefully. H3PO4 could react with water to produce H3O plus and H2PO4 minus. That we would call the first proton process. That's a 4. And that would get us our Ka1. Then this product, H2PO4 minus, could react with water again to get us H3O plus, these are all equilibriums, and HPO4 2 minus. So that would be my Ka, my second proton process, so I call that my Ka2. And then this, which is what we're actually dealing with in this situation, HPO4 2 minus, can react with water one more time to produce H3O plus again, and PO4 3 minus. This is now effectively my Ka3 process. So that's what we're looking at in this particular example. It's the third hydrogen coming off, and so this is going to be my Ka3. And then the second thing that this phosphate ion can do is, instead of acting as an acid, it might act as a base, accepting the hydrogen, and going back to forming H2PO4 and hydroxide. So the question is, which of these two processes is going to be the dominant process? They're both going to happen, but they're going to happen with very different rates. So probably one of them is going to be really effective, while the other one isn't going to be so effective. Now, I'm using a chart from the textbook here, and I can see that the Ka3 for this acid is 4.2 times 10 to the negative 13. But this Kb I don't have. To understand which Kb this is, I have to recognize that if all of these things are written as Kas, this Kb is actually a conjugate process, as in I'm looking at the reverse reaction here. So when I consider that and I look over at this H2PO4, then I'm going to realize that this is the conjugate process for the second hydrogen, or what I would call the Kb2, conjugate Kb2. It's actually the conjugate of this reaction right here. See, here's my H2PO4 going to H2PO4 going to HPO4, and I can see that this was proton 1, so this is proton 2. So since I'm dealing with the reverse of this reaction, I'm dealing with the conjugate Kb2. So with that in mind, I can figure out what that is. I can use my expression Ka, Kb is equal to Kw. So the Ka2 for this acid is 6.3 times 10 to the negative 8. Again, looking at that same chart in the book. So I can solve for the Kb for 2 for the conjugate process. And that's going to work out to be 1.59 times 10 to the negative 7. So this guy is 1.59 times 10 to the negative 7. That means that this one down here, this number is about 1,000,000 times bigger than that number. So this reaction is much faster. So if we consider these two things, this reaction's happening not super fast, but way faster than this reaction. And so since this number is very low, this reaction doesn't really matter. So if I start with some initial concentration of 0.2 HPO4 2- and I want to figure out the pH, then I'm going to look at this process and I'm going to neglect that process. So let's go ahead and do that and finish off this question. Just going to slide down here so that I can get more space and just rewrite. So it is the conjugate process, H2PO4. What am I doing here? 2PO4, going back to that, and becoming hydroxide as it accepts that proton. And the Kb for this is given right here. And I'm saying, just for the sake of having a question to do, that this is 0.2 molar. So that's my initial. I'm going to ignore my initial populations of these. My change, this will go down by x, this will go up by x, this will go up by x. And so at equilibrium, my expressions, 0.2 minus x, x, and x. And this is pretty low, but just for what it's worth for the 100 rule, 0.2 divided by 1.59 times 10 to the negative 7 is about 1,000,000, which is greater than 100. So this change is small and can be ignored. Okay, so Kb2 is equal to the concentration of H2PO4 minus concentration of hydroxide and the concentration of HPO4 2-. So 1.59 times 10 to the negative 7 is going to be equal to x squared, 1x from each, over 0.2. And this can be solved for x. And I got 1.78 times 10 to the negative 4. And that is effectively my concentration of hydroxide. So my pOH in this example will be negative log my OH concentration, which is 3.75. And so my pH works out to be 10.25. So this guy kind of looks like an acid when he's put into the water, but he can, because he's amphoteric, the whole point is he can act as an acid or a base. He can give his last proton and become hydronium and phosphate, or he can take a proton and produce hydroxide. So we got to look at a chart and use the K's to determine which of these processes is going to dominate or which one is the faster process. When we do that, we can see the KB associated with the reverse process is much bigger than that. So when we go to do our pH, we simply focus on the fast process, and then we can come up with the amount of hydroxide that's created, and then we can do our typical stuff where we use that to find the pH. So that's what you can do if you have a substance that could act as an acid or a base, and it's not reacting with an acid or a base, but it's simply existent in distilled water.